Good morning, everybody. It's time again for QBI, and today I'm going to talk about dynamic experiments. And now we're going to use some of the knowledge we have already to work towards an application. And let's see if this works. It's on. Ah, I need to switch that one. So now it switches. So again, some literature. Today, the two new books that would be interesting to look at is image registration principles and spatiotemporal image processing. John Ross always has something to say about everything, so I add him too. And then there are a couple of papers about different topics that we are going to touch today. And in particular, what is here is key point and corner detection, a couple of papers. And also registration is also a topic that we're going to talk about. And now we are pretty far advanced in the class. So we have talked about image enhancements to improve signal to noise ratio. We have looked at the histograms and how they can be improved, what you can get out of them in form of segmentation to automatically segment images. From there on, component labeling to identify different objects in the data, and then see what each object actually represents in the image. And we just before Easter, we also looked into some impacts of statistics and some technical details about data frames and visualization. So we have quite much. And again, the question is, what does big actually mean in big imaging? So first of all, we have a lot of data, as we already know. And the important thing is actually being ready to handle this big data. And with that, we talk about the 3Ds: volume, velocity, and variety. And variety is always interesting, and in particular, if you want to do a statistical experiment. When we talk about volume and velocity, you should try to work towards having scalable methods that are fast and easy to customize to be prepared to work with large amounts of data. And today we have, again, a little bit of motivation and scientific goals of this kind of experiments. And then I'm going to show you some simulations. It's not so easy to show on real data always the principles of these techniques. So we are mainly working with the simulations and prepared examples. And the first thing now is why doing dynamic experiments. What is a dynamic process? So that is essentially something related to objects in motion. Could be cars on the street, could be particles flowing through a porous system, could be a bloodstream, could be an organ expanding and going back again, etc. And what we want to do is to characterize this continuous change or activity throughout the experiment. It also involves real time, and that is to be able to capture the features in the time they actually happen. And there are different definitions what real time is. Someone say it's fast. That's real time. It's not really true. You can do real time also for slow processes. But the question is actually to be able to capture what is happening and to provide the response in reasonable time. So that is also what we're talking about in computing, to get the right information in the right time. For imaging, it also includes some obstacles. For example, we need to be able to capture, store, and manipulate, and also display images from these experiments. So there are many aspects to consider when you talk about dynamic experiments. And there are two types of dynamic experiments. There are continuous experiments that you more or less trigger and something is happening, like rolling the dice you see here in the picture. Or it can also be repetitive experiments. And that's something that is reoccurring with some frequency. And that you can actually use to improve the quality of your data, because then you can trigger your acquisition on a certain event. Could be an engine making one turn, or a fly wing going up and down, or something like that. And by using this in your experiment, you can actually improve the signal to noise ratio, because the same thing is happening over and over again, more or less the same. So that are things you can think about when you plan your experiment, and also for the analysis. You have different approaches how to work with these kind of experiments. So which information would you be looking for in a dynamic experiment? So one thing is, of course, how fast is something moving, or how many particles are present at a certain time during the experiment. And could also be if you're checking sizes of the objects. Then we go back to all the labeling and feature extractions from these items. It can also be that are we moving faster, slower during the time, and could also in the end it can also be something like these particles, are they always distributed the same way, or are they clustering throughout the experiment, or are they going away from each other? These things are questions that we would be looking for in a dynamic experiment. And with the image analysis, we have questions like, how can we track objects between different points, being sure that it's the same object all the time? We can also talk about tracking the shape. So if we truly have identified these objects, are they changing, and how can we look at changes in these parameters? And then we have a lot of different details here, like tracking distributions, topology, voxels, individual voxels, and more detailed is going into the physics, deformation and strain in the object. I'm going to mention towards the end of this lecture, and then there are more general lectures. So these are questions I'm trying to address today. And looking at a little movie here, you can see this is some foam that is bubbling, and you can see some frames of it. This is actually in 4D, so we have volumes repeatedly acquired, so we get the spatial dimensions and the time dimension on the top. And it's not so easy to at least qualitatively analyze this. You can get some idea maybe, but what we would like to see is things like, do the bubbles change in size? Do they different sizes move in different directions, and so on? And not only 4D data can be challenging, but we also have here an example of a water jet, and we want to look at and identify these bubbles that are flying through in the channel. So that would be 3D in a sense, but in this case, we're talking about 2 spatial dimensions and the time dimension. Another experiment where we can look at is coffee making. It's a fun experiment I did long time ago, looking at how the water is moving in this coffee maker, and the movie is online. So if you click on the link, then you can see the whole movie. But the interesting thing here is also how you can extract information. So here I have the image of the original initial state and the final state. You can see in the beginning we have water down here, and in the end we have water up here. And by extracting a slice in the direction of the vertical direction and time, you can see really how these processes are moving. And that can be helpful just for the visualization, but also in real analysis too. Then we have the 3D reconstruction, where we have a lot of data acquired in order to do a tomography. This can be done as also as time series time series of volumes. But the challenge when we have dynamic processes in tomography is the basic requirement of tomography is that things are stable throughout the whole scan. Many years ago, it was tricky to actually keep the patient still so long it was needed to avoid motion. So the main movement patients do is breathing. And just by pulling in the air, your chest changes by several centimeters. And that makes a lot of displacement, which can be a problem. So at that time, they told the patients to keep the breath as long as possible during the scan and hope that they get it good. Nowadays, the scanners are so fast that it's possible actually, and with the help of gating systems, they can actually now handle patient movements. And in the body, there are actually many dynamics. You have the breathing, you have the heart rate, you have organs displacing for different reasons through the digestive system, for example. And all that needs to be covered in a scan. Another case is stage tilting. It's also a tomography case, but it's used in microscopy, where you can just wiggle the plate a little bit, and with that you can gain some depth information. But that's actually a limited data problem, which is sometimes resulting in pretty bad images if you don't take care. And also here, the sample is not maybe completely stable, and that also brings you into trouble. So what we can look at are topics like movement of liquids and mixtures of those. So we have blood movements in arteries and veins, oil moving through porous rock, air through the dough while baking bread, magma and gas in volcano. So there are many such rheology-related processes. And then on the other side, we have deformation to look at, looking at how different items in the scene is responding to some triggering event. And let's see, there it is. So for doing dynamic experiments, you need extra planning. And often you have a lot of constraints, like limited field of view. You can't maybe see the whole thing that is happening in your experiment. Voxel size, so it's about what you can actually resolve. And that's also, of course, related to the resolution functions of the system. The maximum rate of measurements, how fast can you actually acquire your images? Is it fast enough? And that is related to dose limitations, because if you're working with some kind of radiation, it may damage your samples. It happens very easily with high brilliance X-ray sources. Could be a synchrotron already damages, but if you go to free electron lasers, then you burn up your samples while you're doing your experiments. The other side of it is limited flux. That would be you have a very weak source, and maybe you just can't single quantum of information in each frame. So those are the two extremes, and you cannot really, mostly you have to balance different of these requirements in order to get what you want. So on one side, for example, in particular in my case, I'm looking at the neutrons. We usually don't have sufficient flux to do both a very high resolution in time and space. So we have to decide, should our pixels be larger, going for maybe centimeters, millimeters, micrometers. Centimeters is not so realistic, but millimeters or microns is one case. And the other side is going in time, seconds, milliseconds, or microseconds even. What can you do? And that is a balance you have to decide, and you can usually not have both. When you have starting to do your images, then you have several factors that affect the image quality. And one is, of course, the process speed and the spatial resolution. And another one is, a further one is image intensity dynamics. How much intensity can you acquire in the time of the exposure? So just one example here, we have a dose-limited experiment. We have 100 micron pixels, 1 second exposure time, and at the flux I have at my beamline, we get approximately 800 neutrons per pixel. And if you want to maintain the same signal-to-noise ratio, and you want to either go to smaller pixels or higher frame rate, you have to counterbalance that. For the smaller pixels, you need longer exposure time, and for higher frame rate, you need larger pixels. This case is for the neutrons, but in any imaging technology, you have similar limitations. The question is only if your process is so fast that you come into this corner that you need to balance these things. So for example, at the synchrotron, we are probably talking about microseconds and nanometers instead of milliseconds and hundreds of microns. But every technology has its limitations where you have come into this case. So what you can do if you want to improve the acquisition rate is to make larger pixels. So you can tell the camera, okay, I want larger pixels, then you may bin them or resample. The cost of it is that you have a blurred, more boxy image. It may still show what you want to see, so then it's fine. On the other hand, you may want to increase your exposure time, then you have very sharp images. So that is are the two options you have. But every of these measures will result in you miss some small details, either in time or in space. So looking at the frame rates, it's more or less the same problem as we have when we do sampling in a spatial domain. You have two cases. Good sampling, then you have many points along the rise of some change. Then you can capture what's happening very well. In bad sampling, you will only see it wasn't and it is. And in between, you don't see what's happening. But in many experiments, it's actually interesting to see what you have in between. So if you're in this case, then you could possibly even go to an experiment type where you go piecewise constant. That is driving the process to a certain level, letting it stand on steady state at that level, make your images, no rush. And then when you're done, then you go to the next level. Let that go to steady state. And then you take out all the transient effects. That requires, of course, that you can control your process to that level. It's not always possible, and then you really have to go towards increasing the sampling rate. So as a summary, we have the planning of dynamic experiments. If we measure too fast, we will have maybe sample damage. We may miss long-term changes, because if we measure very fast, we also produce a huge amount of data, and it's maybe not possible even to handle that amount of data. So that can be a problem. Most likely, you will also have noisy data, because when you go faster, you have shorter exposure times. And as we know, there is a relation between signal to noise ratio and number of captured neutrons, photons, whichever radiation quantity you are using. And if you measure too slow, then you may miss small and rapid changes, and you will have blurring or motion artifacts in the data, which can be very annoying. Particularly motion artifacts. If you do tomography, you will have very strange streaks in 2D image. You may even have seen it in the evening when you make a picture with too long exposure time. You can see that the hand is sweeping out. That's also a motion artifact. If you go for too high resolution, then we have very few unique structures and in the field of view to track, because the camera is usually limited to a number of pixels. And if you have very high resolution, you only have a tiny field of view, and then you may not see everything that is happening that you want to observe. And if you have too low spatial resolution, then of course you may miss all the fine details in your data. This triangle, I try to visualize what happens if you want smaller pixels. Then you have feature sizes and resolution in this direction. If you want increase the signal to noise ratio, you need to improve either pixel size or exposure time. Or if you want faster acquisition to follow the processes, then you also need to increase the frame rate. So usually you are somewhere in this triangle. You usually don't go for one of these specifics, in particular not the lower ones. This one, of course, if you have a statics example, then you can be in the very top of this pyramid, but otherwise not. This is a very small figure. Anyway, if you have a simple process, then it's a way to analyze it is to extract time-space images. And that is what I showed with a coffee machine before, is that you have your time series, which is actually, in one sense, a movie, but it's also a three-dimensional volume. That means you can slice it in any of the orthogonal planes. So you can, for example, slice it in vertical and time direction, and then you get a nice image that shows how the process or front is moving in the sample. And in this case, you can see that there is in the movie, you can see that there is a dot going up and down. And that dot is on each frame represented at some point. And when you go to the time-space image, you very nicely see that this dot is following some kind of sine-like curve. And this is something I used in one of the experiments we are doing. It's actually a student tutorial that we do at the PSI every year. And now I even have dry run tutorial where you can do everything online, if you like. What it is about is to look at capillary rise in a porous medium. So if you put some porous sample, could be a stone, could be wood, could be a piece of bread, something like that, then the water is pulled up by capillary forces to a certain point. It's when gravity is pulling too much, then it's this law doesn't apply. But in principle, what is happening is this rise that we can see in the movie. What you can see here, it's moving up slowly. Not very exciting maybe, but anyway, you can see that the front is moving up. And if I extract this YT image, you can see that it's really going up very rapidly in the beginning, and then it's slowly converging to some static position. If I now extract the points along this edge, then I can nicely plot them as a function of square root of t. And from that, we can learn about the average pore sizes in the material. All that is in this tutorial. So if you are interested in looking into that kind of experiment, please go there. And another way is to tune your experiment is to run a simulation before. Beam time is mostly expensive or non-available. So you have one shot, 3 days, and that's it. So it's good to be well prepared, and to prepare yourself for the experiment is to run simulations. And one thing is also, it's not only that you have little beam time, it can also even be that you have not your own data even. You have inherited data, so someone else did the experiment already, but someone thinks, oh, we can extract some more information and put another student on that. So they didn't even have a chance to see what's happening. And in order to improve is to run a simulation to check how well, how the process was going and how it worked, etc. And also simulations can also be used for the tuning, to balance to find a sweet spot for the experiment conditions. And of course, simulations are also good to validate and test your algorithm to see what are the limitations of my analysis methods. So what do we start with? We have our cell image again, and we have done a lot of it. We have extracted information in different ways using it with filtering. We have applied segmentations, looked at the shapes, looked at characteristics, and so on. So now we need to do something. Let's say this sample is moving around somehow during your experiment. And now we want to look at different methods that we can work with to identify how it moved and what it did. So there are different methods. One is pixel voxel based. That would be cross correlation, digital image correlation, even add some physics to it, apply transformations, affine or non-rigid transformations. Another way is to make a more abstract analysis. Then we look at key point detection. That is looking at corners and identify how they are moving. And they can actually be very helpful in identifying where an object is moving. And problems we have different thicknesses, we have curvatures, maybe two-point correlation was an example using volcanic rock. So let's start with our simulation. So now we are going into actually looking at the analysis. And we have a very simple little, let's call it, well-aligned cells that are moving. These cells we will want to apply some movement to, and the movement is -1, -1. So you can see that these cells, they are moving well aligned with a small displacement for every time frame. This we want to identify, and that is done. First of all, we need to apply a lot of preparations. So one thing is first applying a threshold, then we need to label each object to know which one we are actually following. Then we may need shape analysis, at least to prepare, to know where we have labels, we have positions, and maybe area, and frame ID. That is the information that we want to put into our analysis. Then we do some distribution analysis and put, well, everything in a data frame. So this is what's happening here. We have our images in an image list, and we label each frame, compute the region properties, and from those, we extract the label, X and Y position, area, and frame index. And that is put into our data frame. That data frame looks like this, the top elements. We have the positions of each object. You can see here that they are nicely positioned. Everyone are on position, the height position 4, and then we have 4, 6, 8, and 10. Each area is equal to 1. It's just one single pixel. It's a small example. And it goes on like this. We have quite many of these rows in the table. And if we sum up all the frames, we can see that it looks like this. We have the color coding is per frame. And you can see that it's nicely moving diagonally up. Now we want to describe this motion, and in principle, what we have produced is the simple vector. We have the velocity -1, -1, and that we want to start looking at how we can measure it and see where it is. And there are several ways of doing it. This is a very simple, let's call it brute force approach that we are going to look at now. It's essentially comparing each item with all the other items and see which one is the closest or least movement, and hope that this one is the right one. This is in principle what we're doing at every point at time in image I0 at time 0, compare them to every point in image I1 at time 1. And then we can see which one is producing the best fit. And that gives us something like this. When we compute each position, this one is connected to everybody else and so on. That looks like a quite messy network. But that can also be put into a table where we can see all these distances. And we can soon sort out that we have a square root of 2 distance, which is the shortest distance between these different objects. All the other ones will be discarded because one object can only be moved to one position. So this is just a little visualization how it's computed. And it's compared. You can see here also the boldness of these vectors is very strong when you have short distance, and the longer distance get more and more faint. So these are the points that we found as the nearest point between frame 1 and 2, or frame 0 and 1 actually. And it's a simple example, so they're not moving in any direction. It could actually be here. If we go back 2 slides, 3 slides. Yeah. Okay, on this one. So you can see here that we could actually have moved this. The distance between this one and that one is actually the same, and it's in this case, in this algorithm, it's pure luck that we actually got the one in the right direction. Otherwise, it can be quite a messy vector field afterwards. So that is also has to be checked. And usually when you do this kind of tracking, you don't do it between just 2 frames, but you look at maybe 2 or 3 frames, 3 or 4 frames to make an interpolation and see which direction is truly the most likely. That's also a classical problem in radar detection, that you have the airplanes on the radar and you want to see where it's moving, and you have many dots. And for that, using techniques called Kalman filters, which more or less have a trajectory prediction already built into the model. So, and then let's track on all frames and we can see how it works. That looks like we have a pretty good matching here, but again, it's pure luck. If we were unlucky, then we would have untracked items and a trajectory which is a bit weird. But in this case, as the -1 is the first one it approaches, we get that one. Another way, so here in this way, we looked at pixels and the constellations and shapes to identify the object. And another way is to work with key points or feature points. Just a little remark back to the pixel example here. I used single pixels, and normally in an experiment, you can also use more information to uniquely identify that this is the right one I'm actually following and not the wrong one. So that would reduce the ambiguous case if there are same distance between 2 objects. But it's not possible if you have single pixels. So yeah, let's do this too. Key points is another way. Now we have looked at the whole shape in our comparison, but key points is about identifying characteristic corners, mostly corners actually, and characterize the shape of the object that we are following by them. And here is one example. We have a raw image, which is this chessboard, slightly skewed. And oh, the color is not good for this. There are red dots on this one. I should have make it better to contrast to that one. Let's see if I can do it. Oh. No, that wasn't meant to be. Okay. I don't try anymore. I should have run the whole notebook to be able to do it. Okay. Let's go back to the presentation. So, no, that was that one. Okay, so another one is to look at the corner peaks on the real data. So this is the bone cell data. And what we are doing is actually we're reading the data and we're using a filter called corner Harris. That's in principle high pass filter, which is very sensitive to corners. And then the next step is to identify the peak coordinates of the corners with some threshold. And with that, we get points where there are corners in the image. So mostly around these black regions here. And that is our way to identify how the image is moving. The idea is that these corner points should be unique, and they are if the sample is only rotating and translating. If the objects are changing in shape, then you may lose these corner features. And yeah, the objects should be quite stable on the other features, and then we can follow it. But this actually also gives us the opportunity to identify each object quite well. And looking at our chessboard, we can see here that the Harris connectors, they are actually pretty good at following these corners. You can see that the green points, they are following every intersection between these squares, even though we are translating and rotating and skewing. So that's good. And the next thing is to work with more a way to identify each corner, because as it is right now, we only have a cascade of dots. And actually, I think I'll save this till after the break. Then it makes more sense. So let's have a break.